In this course, we will consider spaces of functions and study them. The area of mathematics the study spaces of functions is called functional analysis. So functional analysis is the study of functions and their transformations with both algebraic and topological properties. So the viewpoint of functional analysis is the one of linear algebra, but for infinite dimensional vector space. So, however, differently than the finite dimensional case, differently than the finite dimensional case, the possible topologies that one considers will make a difference. In particular, we will see that a sequence of functions can converge to a function in different ways, and this will create different topologies in the space of functions that we will consider. Now, to put a metric on these function spaces, we will consider norms, but one can do a theory that goes beyond the case of norms. So let me just say that in this course, we'll only consider topologies coming from norms. Now we will explain what's a norm, but in general function analysis, the theory goes beyond the case of norms. So we start discussing norms. So normed vector spaces. Okay, so first of all, we only consider real vector spaces, at least for now. We shall consider vector spaces over the real numbers. R. However, it is also very natural to consider the complex numbers But for now, let's restrict to only real numbers. Okay. And as I said before, the most important examples for our vector spaces will be a subset of space of the set of all functions. So subspaces of the space of functions from a set of a space X to R. So we'll denote this as the functions from X to R is also denoted as R to the X, which is the functions f from X to R. Okay, now let's define what's a norm on a vector space. So let V be a vector space over R. A norm on V is a function usually denoted with the symbol of the norm, where this means the entries from the vector space V into 0 included plus infinity excluded, such that for all points x, y in the vector space and for all real scalar lambda, we have the two property. First property is when we multiply a vector lambda, we have absolute value of lambda times the norm of x of the vector. Three properties. Second property, to the norm is subadditive, and three, the only vector that has norm 0 is the 0 vector. And we shall say that in this case that V together with the norm, the pair V and the norm, is a normed vector space. Each norm on a vector space will induce a distance, and more or less every distance with some particular properties will actually come from a norm. So say for vector spaces, the datum of a norm is not so different than the one of an, in quotation, adapted distance. You'll see what I mean. This following proposition. So say V is a vector space. So first, if we have a norm on V, then the function d between x and y, defined as the norm of x minus y, this defines a distance on V that is translation invariant, invariant under translations, and for which the lines say lambda goes to lambda x, as x is a vector in V. These are homothetic embeddings. What's a non-homothetic embedding? I mean that there exists some value c such that the distance of two different images of the curves, say lambda 1x, lambda 2x, is equal to this constant c times the difference in time, lambda 1, lambda 2. So when c is 1, this would be an isometric embedding. Okay, so up to a multiplication of the distance is an isometric embedding. Okay, vice versa, if d is a distance, so is a translation invariant distance on V, for which lambda goes to lambda x, when x is a fixed vector, is a homothetic embedding, or R for every x is a homothetic embeddings, then the function defined as the distance from the zero vector defines a norm on V. Okay, let's prove this proposition. So let's check that the distance defined as the norm of x minus y is a distance, is in fact a distance satisfying the required properties. So this is obviously symmetric. dxy is equal to dyx. It is positive on distinct points, and so strictly positive on distinct points, and that's because if the distance between x and y is 0, we know because the norm is a norm, then x minus y is 0. In other words, x is equal to y. And the triangle inequality. So we have to prove that the distance between x and y is less or equal than the distance between x and another point z plus the distance between z and y. And like if we called this point x prime and this point y prime, then their sum is exactly x minus y. So, and this property, this less than this, is one of the properties of a norm. Okay, so now let's check that then the distance is translation invariant. So, which means that we have to prove that the distance between x plus z and y plus z is equal to the distance between x and y. And this is clear because this is the norm of x minus z minus y plus z, so x plus z minus y plus z, and this is the norm of x minus y. Okay. The last thing, let's prove that line are homothetic embeddings. So on lines, so we have that the distance between lambda 1x, lambda 2x, this is the norm of lambda 1x, lambda 2x, but if the property of the norm becomes the absolute value between lambda 1 of lambda 1 minus lambda 2 times x. Okay, so this is an homotety. Okay, vice versa, the second part of the proposition is so we define the norm of x to be the distance from 0 to x for a distance that is translation invariant and homothetic on lines. Let's check that this defines a norm. So it's a norm since, okay, let's check that lambda x, this is equal by definition to the distance between 0 and lambda x. And now we know that it's a homotety. So this is lambda some constant, which depends on x. But what is this constant? This constant is what we take if we take lambda equal to 1, we get the value of the constant. So Cx is equal to the distance between 0 and x, which is exactly the norm of x. So we proved the norm let you get scalars out with constant, with absolute value. Now, the triangle inequality for the norm, so this is again, the distance between 0 and x plus y. Now let's use the triangle inequality. Since distance between 0 and x plus distance of x and y, x plus y. And now we use translation invariant to, we translate by x, the second term, we have the distance between 0 and x plus the distance between 0 and y, and these are exactly norm of x plus norm of y. The last thing to check is that if you have norm 0, then the vector has to be 0, but this is, we know that d is a distance from, if a point has distance 0 from 0, then the point is 0. Okay, and this finishes the proof of the proposition. Okay. I will make now some important remarks about norms. So, first, whenever you have a norm, then we have an induced distance. And this is the distance we will consider, and the distance induces a topology. So every normed vector space has a canonical choice for the topology. So is the topology induced by the distance? There's no choice in this. But let's pay attention that whenever we have a vector space, then we may equip this vector space with more than one choice of norms, and there are examples of different norms giving different topologies. We'll go back to this point and we'll discuss more. But also, one should know that not all, in quotation, adapted topologies for a vector space come from norms. So in general, in functional analysis, one should consider the notion of topological vector space and do a theory that is more general than the one of norm vector spaces. There are some norms that are a little bit more special than others, and now we will discuss them. So these are those norms that are coming from scalar products. From scalar products. Okay, let's define what is a scalar product. So V is a vector space. A scalar product on V is a function, usually denoted by this symbol, from V times V into R. These dots represented here, they go 2 entries, each of them in V, such that for all triple of points x, y, and z in V, and for all scalar lambda, we have, so first property, the scalar product is symmetric. So the scalar product between x and y is equal to the scalar product between y and x. In each of the entry, you have linearity. So scalar product between lambda x plus y and z is equal to lambda times x scalar product with z plus y scalar product with z. Of course, this and the first one gives also linearity in the second variable. The third property, and notice that here this lambda, there is no absolute value, like there was in for norms. So it's a linear map. The third property is that the scalar product with x with itself is always greater than 0 if x is different than the 0 vector. Okay, so in other words, the only vector with scalar product 0 is 0, and all others are always non-negative. Okay, so a few notes about this definition. So first, so x, y going to scalar product between x and y is linear in both variables is linear in both x and linear in y. So this is said it's bilinear form. Second thing is a scalar product. I will just rephrase the definition. So a scalar product is a bilinear form. This gives condition 2 that is symmetric, and this is the condition 1. And positive definite. Very well. So we call that this is positive definite, and this one here is symmetry. Okay. Okay.